Welcome to the NERI SimCenter's live expert tips, July edition. My name is Laura Lowe's. I'm a faculty member at the University of Washington and a member of the NERI SimCenter leadership team. The SimCenter Live Expert Tips is a venue where we feature the capabilities of SimCenter tools through compelling examples and use cases in natural hazard engineering simulation. In this session, we'll introduce you to a unified framework and library for hurricane risk simulation. And our expert today is Ms. Rachel Hamburger. Ms. Hamburger is a PhD candidate in civil engineering at the University of Notre Dame and a graduate student intern at the NERI SimCenter. Her research aims to expedite learning from disasters, which begins by documenting building damage post-event, with analysis and dissemination subsequently occurring through the disaster data to knowledge life cycle. At the SimCenter, Rachel contributes to integrating high-fidelity granular hurricane risk assessments into the center's computational ecosystem. Originally from New Jersey, Rachel holds a BS and MS in civil engineering from Lehigh and is working on her PhD at Notre Dame. Welcome, Rachel, and thanks for being here.
Great. Thank you so much, Laura, for that introduction. And thank you, everyone, for joining me here today for the SimCenter's Live Expert Tips. As Laura mentioned, the title of my presentation today is a unified framework and a shared model library for hurricane risk simulation. So I'll just start off with a brief motivation. Increasing severity and frequency of storms coupled with population surge has led to rapidly increasing risk for vulnerable communities. Numerical simulation is needed in order to quantify risks and that are used to inform mitigation strategies and provide risk information to citizens and stakeholders. However, the conventional models used for this sort of simulation were designed and are used for large-scale, low-resolution studies, while the more complex models and data used to calibrate them are part of largely proprietary systems. Now, there are many examples of research advancing beyond the traditional. However, the organic evolution of this field has led to several coexisting state-of-the-art techniques. Thus, we propose our unified approach, which presents a standardized vocabulary and framework, enabling a better understanding of gaps, needs, and capabilities in this research area, while facilitating integration through our shared parameter library. So, throughout this study, we were particularly interested in understanding how high-resolution hurricane risk analyses were performed. Historically, regional risk analysis and performance-based design were developed independently, with the former relying on more simplified models to assess large building inventories, and the latter focusing on more detailed assessments of individual structures. However, with modern high-performance computing capabilities, these assessment methods are beginning to converge, enabling high-resolution hurricane regional simulations. And so, therefore, it was our objective to bring these granular damage and loss models into the SimCenter's existing infrastructure. Now I'll touch on just a brief outline of my presentation. I'll start with an introduction to our generic framework before moving into its applications to different hurricane hazards. I'll then describe what demand and damage calculations look like for each of our 3 hazards, with only a brief description of loss calculations. And finally, I'll conclude with a discussion about data. Now, for this presentation, I'm going to forego conversations about hazard characterization in the interest of time. But if you're interested in learning more about this step, we are publishing a manuscript which includes detailed descriptions about that. Throughout this study, consistency in vocabulary remained a top priority for us. We paid careful attention to all of the terms in literature and used this to inform a cohesive dictionary of the vernacular that we use throughout our study. The table on the left is a list of all of the vocabulary that we define in our manuscript. And I'm not going to go into detail about each of these, but I do want to highlight 3 key asset definitions that are very important to understanding the framework. The first is a component, which is the smallest functional unit of a structure and includes examples such as a shingle, a window, or a single roof-to-wall connection. The next is a subassembly, which is a class of components that all function together, such as all the roof cover or all of the roof sheathing on a structure. And then finally, we have a building, which is the entire structure comprised of multiple subassemblies. Now, keeping these in mind, I'm going to continue to introduce some definitions as they are relevant throughout the presentation. Okay, let's move on to the introduction to our generic framework. The architecture of the framework could be understood as a matrix, with columns representing steps that follow a performance-based engineering setup, including event characterization, engineering demand, damage, and loss. Rows are decomposed by resolution, and they describe whether analyses are performed at the component, subassembly, or building level. Each step is comprised of a unique group of nodes, and nodes are labeled according to their function. At the top, you'll see our input data nodes that have a label of D. And though the specificity of input information will probably change depending on the resolution of the model that you're using, the input data nodes are meant to describe the minimum information needed for each step. Next, our gray rectangular boxes are our method or model nodes. And available model nodes are informed from those commonly available in literature, and they vary in terms of specificity of input, the resolution of the output, and different parameters or calibrations. These nodes are labeled x.y and represent a model or a method at x step for y resolution. In yellow and with a label of S, we have our output nodes, and each step can have multiple output nodes for different resolutions. And finally, in orange, we have our mapping nodes with a label of M. Mapping nodes allow for communication between different output resolutions, allowing the user to traverse easily between component, subassembly, or building-based assessments. Putting that all together, we arrive at our final product. Now, you'll notice from this figure that the framework is not specific to any one hazard, but with a thorough enough understanding of the literature, it can be applied to different hurricane hazards. So that's exactly what we did. We performed an extensive review of 3 hurricane wind hazards, and then we used what we learned in order to populate that matrix for each of the hazard contexts. Before I show you those populated matrices, I want to introduce you to the 3 hazards that we looked at. The first is our wind-induced pressure, which is the direct demand on a structure as a result of the aerodynamic interaction between the structure itself and the surrounding wind field. Next, we have windborne debris, which is when debris items are generated in the surrounding environment and carried by the wind to eventually make impact with a structure. And then finally, we have wind-driven rain, which causes rainwater intrusion into a structure. Now, obviously, there are many other hurricane hazards, such as surge, inland flooding, floodborne debris, wave action. But for this study, we focused only on wind-induced hazards. However, remember that the original framework is generic. So theoretically, in the future, hopefully we could populate matrices for those hazards as well. Now, as I show you these populated matrices, try to not get bogged down with trying to understand all of the individual details, because throughout the presentation, I'm going to periodically come back to these figures to ground us back to the original workflow and remind us where we are in it. I start off here by showing you our wind-induced pressure matrix, and this analysis is fundamental to hurricane risk simulation. The density of models in these frameworks are dependent on the quantity and diversity of research in the specific hazard area. And in our review of literature, we tended to focus on studies that employed high resolution techniques. However, we did review a diverse body of work. Next, we have our windborne debris framework, and you'll probably notice right off the bat that this matrix does not have a loss step. And this is because in loss analysis, the cause of the direct damage is not typically considered. Instead, our loss calculations are dependent on a cumulative total damage incurred. And because of this, it eliminates the need for additional loss models in the windborne debris matrix. And then finally, we have wind-driven rain. And though wind-driven rain does not cause direct structural damages or losses to our building, the resulting contents and interior loss are substantial. So accordingly, most of the work in quantifying wind-driven rain loss effects are focused in the loss section. Okay, now that we have a solid background on our generic framework and our hazard-specific matrices, it's time to have some fun. We're gonna take a deep dive into several of the steps for all three hazards, starting with engineering demand. Engineering demand is quantified by engineering demand parameters, or EDPs. And EDPs are response quantities that can be used to directly measure the performance of a certain component, subsystem, or system when exposed to hazard loading. I'm sure it comes as no surprise, but the EDP for our wind-induced pressure analyses is the pressure or the resulting uplift forces on the structure. In this step, we take some measure of hurricane wind speeds and feed it into either empirical or physical demand models to calculate this pressure. So let's take a look at some examples of those. The most common representation of an empirically calibrated pressure equation is gonna go ahead and be our ASE 7 equations. And ASE 7 presents a procedure for simulating wind pressure on either the main force resisting system or the components and cladding of a structure. And these equations are dependent on our internal and external pressure coefficients. These coefficients can be sourced either directly from the standards or they could be taken from alternative sources such as databases. Now, because these equations are used for design, they often provide a conservative estimate for pressure. So researchers, because of this, researchers have proposed using a modified ASE 7 equation to remove that embedded factor of safety. Next, our physically derived pressures would come from either experimental wind tunnel tests or more complex numerical simulation like computational fluid dynamics. And I want to note that larger and more complex structures will probably require these more robust wind pressure models, as well as additional EDPs may need to be considered, such as interstory drift or accelerations for buildings that are dynamically sensitive. Okay, now let's move on to windborne debris. And the EDP models for windborne debris exist in both the component and subassembly levels. The component EDPs are separated into two distinct steps, including the generation of a debris object and the flight trajectory of that debris object. Again, we'll start by defining some vocabulary. So on the component level generation models, a source building generates debris that will eventually hit a target building of interest. Debris generation can be modeled explicitly at the component level through a pressure analysis of the source building. And to do this, you would catalog the components that fail and subsequently become airborne. Now, obviously, there are many different debris types, but ones that are commonly considered are roof cover, roof or wall sheathing panels, or rooftop gravel. Once the debris is generated, we then have to model its flight trajectory. Physical models trace the trajectory of debris objects in three-dimensional space by solving the equation of motion. But a less computationally expensive option is to use empirical formulations. For example, some researchers have proposed sampling the degree landing position from a Gaussian distribution. And if the trajectory of the debris object intersects with the target building of interest, then the velocity of that missile at impact will be used to find two possible EDPs. One, either the impact momentum or the impact kinetic energy. Finally, let's take a look at what EDPs look like at the subassembly level. And I want to note that this is a methodology that was originally proposed for the Florida Hurricane Public Loss Model. Here we're finding the total number of debris impacts on a structure as the product of four independent factors that are calculated based off of wind speed. And those factors include the fraction of potential missile objects in the surrounding environment, the total number of available missile objects, the fraction of airborne missiles that hit the house, and the fraction of the impact wall that is going to be vulnerable to those impacts. Finally, the EDP for wind-driven rain calculations is the height of ingressed rain. And one important thing to note here is our change of inputs. Even though wind flow effects are certainly important to consider for this analysis, wind-driven rain calculations require some measure of rainfall intensity. I'll briefly step through an empirical process for calculating the height of ingressed rain. It begins by finding some measure of the horizontal impinging rain on a structure. We then need to obtain values that are specific to the individual building and the event itself. The first of those is called our rainfall admittance factor, which captures the effects of the building geometry and also the aerodynamic interaction between the building and the wind flow. And then next we have our surface runoff coefficient, which captures the rain and that runs off the building facade. Finally, once we have those factors, we can use empirical formulations to calculate the total volume of rain that is ingressed into the building. And here we need to consider rain that penetrates through either pre-existing defects in the components of the structure or through breaches of the building envelope. Now, I'd like to end this section with a brief discussion about EDPs in general. The EDPs enable higher resolution studies of specific feature performances, and they also result in reduced uncertainties in subsequent damage calculations. However, when you introduce EDPs into your risk analysis, you are adding an extra step. So this will increase your computational expense and also requires more detailed input data. And you might notice from this slide that it looks a little bit like a pros and cons list, but I am specifically not using those words because through this study and through this presentation, we never wanted to advocate for a certain or a specific methodology because not all methodologies are appropriate for all problems. But rather, it was our goal that by understanding the different pathways and the different models available through our frameworks, a user would be able to assess their needs and decide whether a high resolution analysis that does require EDPs would be appropriate for their specific context. Okay, the next step we are going to look at is damage. And before we dive into the hazard-specific applications, I want to briefly review fragility functions, though I'm sure most of you have at least heard of these before. Fragility functions are the basic mechanism for most damage assessments. They're the conditional distributions that describe the probability of exceeding a limit state capacity given an intensity measure such as wind speed or a demand parameter like pressure. And they typically adhere to either normal or log normal parameterizations. Okay, now let's look at wind pressure induced damages. And again, I am reminding us here of our current position in the framework. And for wind induced pressure, we have models at all three resolutions. And we also introduce a mapping node between subassembly level damages and building damages. Remember our definition of component, which would be a window or a single shingle. Component unit fragilities take wind pressure or some other EDP at input, and these functions are typically confined to describing binary damage states, such as those that inform either the occurrence or non-occurrence of failure. Component fragilities are calibrated through experimental testing, and they can be found in places like manufacturer documentation or published studies. Now I'm going to pull these next two up together. But subassembly fragilities are describing the damage of a class of components, remember, such as all of the roof cover on a structure. And building fragilities are describing damage to the entire building. And they're usually available for archetypical structures. But the input to both of these fragilities would typically be an intensity measure, which is wind speed in this case. And they are usually available for multiple damage states that usually describe an increasingly severe range of damage. And these fragilities are typically calculated with either historic damage data or numerical simulation. Okay, now let's talk about that mapping node. The mappings are created with the underlying understanding of how structures typically fail in hurricane hazards. And so I love this figure on the left, which is from Pinelli et al., that shows this kind of intuitive engineering judgment on how structures fail with a series of Venn diagrams. So the circle that has an O represents damage to openings, and then damage to roof cover is represented by a label of T. And you'll see that these two circles occupy the largest subset of space in the Venn diagrams. And this just indicates that damage to other components like roof to wall connections won't occur before damage to openings or roof cover. But how does this manifest into actual quantifiable mappings? So I show a very popular example on the table on the right, which is taken from Vickery et al. And was made for the HASIS platform. And you could see that the building damage states, which are highlighted to the column on all the way to the left, are assigned based off of the cumulative damage to all of the subassemblies. Okay, next we move on to windborne debris damages, which also has models at all three resolutions. Our component damage models can either be explicit or implicit. The explicit will take either impact momentum or impact kinetic energy as an input and return, again, the single damage state that informs the occurrence or non-occurrence of failure. Our implicit model will describe the probability of at least one component failure from impact, and this is modeled as an exponential function, with our input being the total number of debris impacting the building. So that subassembly level EDP that I talked about a few slides ago. And again, I'll bring these up together, but at both the subassembly and building levels, windborne debris damage can be modeled implicitly. So if the fragility functions were calibrated with data that from either high resolution simulations or post-disaster damage surveys that capture the damage from our windborne debris, then this would constitute an implicit model of windborne debris damages. And so here the fragilities take wind speeds as input and also describe a set of increasingly severe damage. Finally, I'll talk about the wind-driven rain damages which occur only at the component level here. And this methodology requires a detailed knowledge about the layout and also the specific contents that are in a structure. This figure and table are taken from a study by Park et al. And in their methodology, they knew the exact layout of the structure and modeled the individual contents of the house. And then contents interior were subsequently damaged by the ingressed water. So note that by doing this, you probably vastly decrease the uncertainty in subsequent loss calculations. However, this level of detail is probably impractical for large-scale simulations. So far, we've looked at damages for each individual hazard, but what happens if we want to consider hazards together? How can we model this cumulative damage? So this figure shows how we can do a combined damage analysis at the component level, which involves an iterative analysis where demand and damage are coupled. If the building envelope is breached by either wind pressure or debris impact, then the building will experience internal pressurization, and therefore the pressure should be recalculated and the asset needs to be rechecked for damage. And this will continue until the building reaches a steady damage state. And then you can find the cumulative damage as a result of both debris and wind pressure. At the subassembly and building level, what this looks like is that you need to know if the windborne debris is implicitly modeled in your damage models. And if not, it needs to be captured in some other explicit way. And just a final note is that wind-driven rain damage is always additive, so it's not shown here coupled with the other damages. And because of time, I'm not going to go into detail about our loss calculations, but I do want to show you just the overview images to prove that we did similar groupings of loss models. Remember that for losses, we can combine the damages from our wind-induced pressure and our windborne debris. So here we have 4 options for loss modeling. And we also have, interestingly, introduced a kind of a reverse mapping, where if you are performing a building level damage and loss analysis, you can take those building level losses and map them back up onto subassembly level losses, which would be useful if you would want to inform things like specific repair actions in your model. And then for wind-driven rain, as I discussed, most of the existing methodologies actually do concentrate in the loss modeling. And so here we have options for all 3 resolutions. Okay, and I will end the presentation with a very brief discussion about data and our shared model library. Okay, as I mentioned in the beginning of the presentation, we reviewed a significant body of research for this study. And so far, I've only discussed how we can organize these works into a cohesive schema. But we were also interested in how we could make these types of simulations more accessible to the general research community. And to at least start doing this, we are publishing 2 supplementary materials along with our manuscript. The first is a database of all of the papers that we reviewed for each of the 3 hazards. And this database will include a unique sequence assigned to each paper that represents the pathway of nodes it takes through the respective framework. And then we also compiled a very comprehensive set of calculations and models and parameters. And so this figure on the right is just a screenshot from that document of component unit fragilities. And as you can see, there is extensive information about the asset, the limit state fragility parameters, and of course, citing the original source. Now, these libraries are in the process of being added into the SimCenter's publicly available damage and loss database, though I need to stress that they are not currently live or open to the public yet. But when they are available, you'll be able to access them through the GitHub page, which is the QR code on the bottom left, their damage and loss database. And then the data that is in the damage and loss database will be eventually used by Pelicun. In the coming months, the Pelicun engine will be able to run all of the described analyses, including our high resolution simulations. And I'll just close with a few words about data sharing. So our compiled libraries and databases are really intended as living repositories for our research community. In a lot of ways, the seismic community has already successfully done this with fragility parameters and consequence functions for seismic analysis organized and disseminated through FEMA P58. So my final message would be to please use this data, leverage the models that are already existing. And if you have your own data that you want to add it to the database and share it with others. Here are some references that I cited throughout my presentation. And lastly, there are so many people that I need to acknowledge for this work. I want to thank all of my collaborators for their wisdom and their advice and all of the contributions that they made to this project. I want to extend a special thank you, though, to my mentor and co-creator of this work, Adam Zarnowski. And I also want to thank the NSF SimCenter and the University of Notre Dame for their support throughout my PhD research. And thank you to all of you for joining this presentation today. Before we jump into questions, I want to plug very quickly that if you would like updates on the manuscript or when that data goes live, my email is on the screen. Shoot me an email, connect with me on LinkedIn, and I will be sure to keep you in the loop for all of those things. Okay, so now thank you, and I will take questions.
Thank you so much, Rachel. That was really interesting. There are a couple of questions that are in the chat. Can you see those, or do you want me to repeat them? So how about if I just read them, because I can see them clearly right now. So one of them is the component to structure damage mapping considered one hazard parameter at a time or combined from component damage from all hazards?
Yeah, that's a really great question. I think that it could be combined with the windborne debris and the wind pressure analysis, as I showed that combined analysis where we're considering cumulative damage from. Actually, let me just go back to that slide. Here we go. If we consider the windborne debris and the wind pressure at the same time, then we can kind of result in this cumulative damage measure. And our mappings are just kind of a direct pathway to building damage as a result of the cumulative damage to subassemblies. So theoretically, they could be used for an independent hazard, or they could be used in this combined analysis, just depending on what you're considering in your own formulation.
And then the second question, I saw a second question. Okay, I will ask a second question. And I guess that kind of goes to the first question, but I'm trying to relate it to earthquake engineering because that's my area of expertise. So there's an enormous amount of computation, even at the individual structure level. And I guess I'm curious to know, like, is there a break in the path of assembling and thinking about all the different damage that's accumulating, where you say, oh, this is sufficient damage that the structure is a total loss, or that I've reached some point where I don't need to do any more calculation, it's gone?
Yeah, absolutely. I think that these damage thresholds, I guess, for lack of a better word. There are established thresholds that are implemented already in kind of these large off-the-shelf softwares like HAZIS or the Florida model, where it is implemented more in the high resolution models that calibrate those systems. But essentially what they do is that they have their building level damage states that are assigned based off of more high resolution or granular damages to our components or subassemblies. But they implement a threshold that would say, okay, as soon as our roof sheathing exceeds 25%, then we know that we're going to have to replace all of the roof sheathing on the structure anyways. So the loss for roof sheathing would then go to 100% because we're going to have to demo and replace everything anyways. So
Okay.
there are those that are kind of common practice in the community that are used, and you kind of have to dig for that information in like most data, you have to dig for it in the manuals and see, what are the thresholds that they are considering there.
Okay, thanks. Second question, where within the framework do you think is the greatest need for additional research?
That is a great question. Thank you. Thank you for asking it. I think from my from what I noticed in my research is that there is the least consensus in the loss step. And I think there's a lot of reasons behind that. Maybe paramount is that there's just so many things that should be considered in a loss analysis. Obviously, the most easy to conceptualize is our direct structural losses, right? Because it kind of presents that 1-to-1 ratio between damage and loss. Whatever components are damaged, you know that this is their replacement cost. But there are things that are a little bit harder to quantify, such as the losses to the interior and to the contents, and they vary so much from household to household. And then as well, there are things that don't maybe have direct physical costs, but have indirect economic costs, such as all the social costs of hazard damage, like displacement or downtime, if we're talking about commercial buildings, injury, death, all of those things that are really not typically considered what I see in simulation. So there's a lot to unpack, and I think that among the literature, there's the least consensus about how we should do those loss simulations. So I think maybe work there in quantifying all of these different loss values is important. And without going on a tangent, I will add also that the loss models are often hardest to make because the data is sparse. A lot of the loss models are calibrated with insurance claims data, and that data is proprietary often or needs to be purchased. Or includes sensitive information and can't be distributed publicly. And also, if you rely solely on insurance data, then you are not accounting for those social costs, as I mentioned before. So I think there's a lot of interesting questions to consider for loss right now.
With that, I'm going to say thank you very much